Hi everyone, my name is Wei-Yao. I'm a PhD candidate at National Jiao University. This is a recording video for what will players' move lengths, dynamic graphs, and hierarchical fusion for movement forecasting in badminton. This is a joint work with Kai-Shang Chang and Professor Wenji Peng. First, how to know players' tactics from matches. The simple method is to collect historical records to visualize and analyze the results. For example, if the goal is to investigate the shooting patterns of Stephen Curry between two seasons, we can collect the data and observe the similarities and differences between the visualizations. On the other hand, the effective way for investigating the advanced tactics is to analyze the matches by domain experts who are able to uncover implicit patterns with their domain knowledge. For instance, in the World Cup final, the tactic of Argentina adopted a structured lamp max implementing a possession-based style of play slightly easier than some other formation when possessing the ball. In general, these methods are called sports analytics, which benefits the performance of teams or players on the field by applying the data-driven methods like strategy recommendation and scouting report. Recently, the rapid advancement of technology has brought great convenience for data collection and increased data diversity, which also enables sports analytics community to analyze microscopic tactical applications. In this paper, we focus on one of the turn-based sports, badminton, which has been carried out to develop on-field and off-field analytics for improving player performance and boosting fan engagement respectively. To investigate the performance of players, we focus on on-field analytics, and existing work for on-field analytics mainly targets on quantifying stroke performance and predicting future shot types and the corresponding locations of the return stroke. However, in badminton, as a fast-paced sport, in addition to returning strokes, players' movements on the court are also a critical factor of simulating tactics, which hasn't been addressed in prior works. We name this task movement forecasting. As an example in the slide, each step consists of the location of two players and a shot type. Given the locations of two players and a shot type they performed in a rally, the player on the right has several options of shot type and location to return the shots and move back to defense, while the player on the left also has multiple choices of location to catch the shuttle based on the location the opponent is returning to. Like, the right player can either return a net shot and take a defense position closer to the net to prepare for another net shot, or can return a lob to the backcourt and move to the center of the half court to prepare for the smash. So generally, movement forecasting can be viewed as a more challenging task since the goal consists of not only stroke forecasting, but also the movements of the players for reflecting the physical ability and the defensive position habits. To address this task, a potential solution is to frame movement forecasting as a sequence prediction task, and then it can be tackled by sequence-to-sequence models. However, sequence-to-sequence models are ineffective in terms of modeling the heterogeneous interactions between different players and the relations between the same player at different time steps. For example, a net shot causes the opponent to move toward the net. Consequently, the player has less time to go back to defense due to the short flying time. On the other hand, a lob moves the opponent to the backcourt, which enables the player to have sufficient time to move back to defense. To mitigate these limitations, another approach is to represent a badminton rally as a graph with various relations to describe different purposes of the movements across different time steps. Still, there are three key challenges that hinder the direct use of existing graph methods in movement forecasting. The first one is how to construct a graph to represent rally information, including the relations among players and their strokes. Since previous approaches haven't adopted graph for turn-based sports analytics, there is no existing method for reconstructing badminton rallies into graphs. The second challenge is how to model dynamic tactics such as the styles and tactics of both players in different rallies and even within the rally. Players often change their tactics to avoid their strategies being seen through, so it is not suitable for fixedly model the styles and tactics of both players. Third, multifaceted aspects. To decide the next action, players consider not only the tactical preferences but also those of their opponents. Also, players are confronted with different significance between styles and rally progress according to the current circumstance. Next, we are going to talk about our proposed method, DYMF. Here is the problem definition. Given the past observed strokes consist of players' shot types and the players' locations, the objective is to predict future strokes in the rally, including shot types and the locations of the two players. This is the overall architecture of the proposed model, which is an encoder-decoder architecture where the encoder encodes the observed stroke sequence, while the decoder recurrently generates the locations of two players and the shot types they perform based on the encoder context. Specifically, both the encoder and decoder include four modules: an embedding layer, our proposed PN graph, an interaction style extractor, and a hierarchical fusion. Then, the fused outputs of the decoder are used in the movement predictor to predict the locations of both players and the shot types they performed. Next, I will describe these modules in detail. The first one is the player movement graph. As a rally consists of players hitting the shuttle back and forth, the interactions between players within the rally can be described as structural representations in a graph. Therefore, the graph construction procedure represents the rally progress as the evolution of a series of undirected multigraphs. Let's first define nodes and edges for the graph construction. The nodes in the graph are the locations of the two players from the first time step to the current time step as shown in the figure. And the edge represents one of the strategic relations, 10 of which are shot types, and the distribution are as the figure. Another relation is return, which links the nodes of the same player at the time steps t-1 and t when the purpose of the movement is to return the shuttle. The last relation is defend, which links the nodes of the same player at the time step t-1 and t when the purpose of the movement is to return to the defense position. Here we illustrate an example for constructing the encoder graph. At the first time step, there are two nodes that represent the initial locations of the two players before the rally starts. Afterwards, at each time step, two nodes and three edges are added to the graph to represent the movements and interactions of players on the court. The three new edges contain one shot type that links the node of the player who returns the shuttle with the time step t-1, and the node of the player who will return the shuttle at the next time step. One defend type that links the nodes of the player who returns the shuttle with the time step t-1 and t, and one return type that links the nodes of the player who will return the shuttle at the next time step with the time step t-1 and t. Next, we move on to the embedding layer. The embedding layer takes the locations of two players and the corresponding player's information to calculate the initial representation of a node with linear layers and activation functions. In the decoder, the new nodes are the locations of the two players at the last time step. To model the styles and tactics of both players dynamically, the interaction style extractor is introduced with the relational GCN and dynamic GCN to capture the interactions between players and the individual style of both players respectively. Specifically, both the shot types by either player and the purposes of the movements influence the next locations of both players. Moreover, the relations between the same players are heterogeneous as well. For example, we can see that the distributions between returning and defending strokes are different because of the tactics from both the players and their opponents. Therefore, the relational GCN is a propagation model that learns the node embeddings by aggregating the information from neighbors based on the relations between them and the self-connection. To stabilize the planning of each relation, we adopt the regularization method of basis decomposition by using learnable parameters of each relation for the basis matrix. Previous work for stroke forecasting demonstrated the importance of considering player styles by ignoring the dynamic personal styles of each player, which is frequently changed at each stroke for adjusting their tactics. Therefore, we propose dynamic GCN by generating the weights based on the player's patterns to capture dynamic personal style. Formally, we apply a 1D CNN and bidirectional LSTM to capture the local and global movement patterns of each player respectively. The outputs from LSTM are then used as the weights of GCN to calculate the context of player interactions for each node. In this manner, the weights are generated dynamically based on the player's pattern. After generating context of rally interactions and player styles, let's talk about the mechanism for fusing this hierarchically. The intuition is that Although players move to the next location for returning the next row based on rally interactions and player styles, we can expect that the importance of each varies under different conditions. But why do we need to fuse hierarchically? The reason is that the player styles from the outputs of dynamic GCN are independent of each other, so we need to first fuse them to measure the influence of each other. Therefore, we propose the hierarchical fusion to decide the mutual importance of each styles, and to merge the context of rally interactions and player styles with player-to-player fusion and player-to-rally fusion. Specifically, the mutual influence of the style of each player are computed from the outputs of dynamic GCN using player co-attention. However, instead of using the outputs directly, we transform the outputs of player co-attention to the overall influence for dynamically indicating the importance from the opponent's styles to the players themselves. Afterwards, the player-to-rally fusion takes the outputs of player-to-player fusion and the outputs of relational GCN to determine the corresponding dynamic weights with reasonable weights. Then, the propagated node embeddings are updated based on the dynamic weights. To predict the shot type and the locations of two players, movement predictor is adapted for them. The first step is to predict the shot type at time step t. The outputs from hierarchical fusion are concatenated and then transformed with a linear layer to classify the shot type, which is a newly added edge in step 2 of the PN graph. To predict the locations of the two players at the time step t, we follow previous work to learn a bivariate Gaussian distribution for the location of each player. Specifically, each output consists of the mean, the variance, and the corresponding correlation coefficient of two-dimensional coordinates. To train the model, the objective function is designed to minimize the shot type, cross-entropy loss, and the negative low likelihood for each player location. In the experiments, we use a Badminton dataset from previous work to measure our proposed method and demonstrate the idea of movement forecasting. To examine the performance of our model, we compare our model with both sequence-based models and graph-based models on different observed stroke sequences. We denote PM as a substrate of the graph-based method if the baseline use our PM graph for encoding. We use mean square error and mean absolute error for location metrics and cross-entropy for shot type metric. We can say that our model consistently outperforms our baselines in terms of all metrics and different observed trends. Let's delve into the observations. First, sequence-based models like sequence-to-sequence and transformer degenerate location performance compared to graph-based methods like GCN and RGCN. This not only indicates that naive sequence-to-sequence models fail to model structural information between locations, but also demonstrate the importance of applying the PN graph to capture the influence on the intent of movement. Second, DNRI hinders all performance more significantly, although it dynamically models the relation between two players. This implies that two same nodes for representing two players separately across time is insufficient, and again raises the need for using the PN graph with new location nodes. Last but not least, we can observe that ShuttleNet outperforms all groups of baselines because it is designed for turn-based sequences. Nonetheless, our DYMF still performs better than ShuttleNet, which is attributed to our interaction style extractors for modeling mutual interactions across time and the dynamic tactics based on the previous movement patterns. This comparison reveals the importance of considering the purpose of players' movements. Next, let's talk about two scenarios for the movement forecasting task. This is a case of investigating strategies in different defense locations. The red node is the player who serves the rally, and the blue node is the opponent. Counters are the location distribution of each player at the next stroke. Given the 3 strokes, the player is going to return the shuttle. In the original defense location, player B plans to return a net shot, which leaves the player A in a passive position, and thus has fewer choices for returning the stroke. However, after changing the defense position to the near front court, player B is probably to return a clear to the backcourt, which gives player A an opportunity to launch an attack. This case illustrates the opponents return the shuttle based on the defense location of the player. Therefore, standing at an effective position blocks the choices and forces the opponent to return a predictable stroke. The second scenario is to investigate different strategies against the same player. Similarly, given the 3 strokes, and we aim to observe the tactics of both players at the 4th stroke. From the figure below, we can see that player B is likely to return a clear to mobilize player A to the backcourt, while player C is more likely to return a drive straight to player A, which is more aggressive than player B. As a clear has a longer flight time, player B has more time to move to the defense position, while returning a drive has a shorter moving distance. From these cases, our DYMF is able to reveal not only the strategies of defending locations, but also the strengths and weaknesses of players, which provides multifaceted usage of movement forecasting. In conclusion, we introduce a movement forecasting task, which predicts the player's future movements and the shot types. To address this task, we propose DYMF with the PM graph for transforming rallies with strategic relations between players' locations. The interaction style extractors aims to extract mutual interactions across time and capture dynamic tactics based on the player's past movement patterns. Furthermore, the hierarchical fusion is designed to integrate mutual influence of styles and interactions to decide the next action. From the experiments, our model empirically demonstrates the effectiveness compared to both sequence and graph-based approaches. Also, we illustrate two cases to provide the practicality of movement forecasting. That's the end of my presentation. Thank you very much for paying attention. You can scan the QR codes for paper codes and my contact information. Please do let me know if you have any questions. Thank you.